Okay, again with the Energy Pool Module 7.3. Problem states a spring with a spring constant of K equals 80 newtons per meter is compressed 0.3 meters, and a 0.2 kilogram book is placed on top of the compressed spring. So our first problem is draw a picture of this process. What are the initial and final states of the process? What is the reference we are trying to use? So let's start off. Here's our level of reference that we're going to use. We have our initial process. So here's our initial here. We have a spring that is not compressed. And we're going to assume that this spring has no mass. So we can write that on here. Assume M of the spring is equal to 0 kilograms. And that'll help us later. The next state will be the spring is going to be compressed, so we're going to be pushing this spring down like this, and the spring will then be compressed here. And so I'm also going to make another assumption here that when the spring is compressed all the way down, it will actually be compressed to the ground level. That'll help us out quite a bit as well. So I'll just have this drawing here. This is the actual spring, but our height here, h is going to be 0 because it's compressed all the way to the ground level because we wanted to make the ground level our reference. And then in our final state, we are just going to have this compressed spring here, and we are going to have a book placed on top of this spring. And again, the height of this book is going to start out as 0 meters. So that's a picture of our first. And again, reference level we're using. We are using the reference level that h, our height, is going to be equal to 0 meters. So that's at this ground level right here. So throughout the whole thing, that's our reference. So what will happen when the spring is released? So when the spring is released, of course, the spring is, since there is this now elastic potential energy in the spring because we've pushed it down, it's going to want to spring up or fly up. So initially we have a high elastic potential energy. We're going to be going to some kinetic energy. So as our initial, this is our second step. So we can say first step, second step, or I for initial. It's fine. We're going to be going to some elastic potential energy. There's going to be some kinetic energy because now it's in motion. And there's also going to be some gravitational potential energy because the book is going to be flying up partially above the ground. And in our final stage, part 3, we could say final, we're going to have 0 elastic potential energy. We will have a high amount of kinetic energy, actually the maximum amount of kinetic energy. So if we want to actually write that in here, high kinetic energy. And we're also going to now have a higher amount of gravitational potential energy because it will be higher above the ground. So part C says draw a picture of this process. So we'll draw these three processes from initial to final states. So let's start off with our ground level like we did before. And our spring now is compressed. The book is on top of our spring. Remember, H is going to be 0 at this point. And this is our initial state, or phase 2, or phase 1, I'm sorry. In phase 2, it will have raised a little bit, still compressed, but have raised a little bit. And the book will still be on top of our spring. We're at some height now. We don't know exactly what that height is, but we're at some height above ground. And so that will show us that there is still some elastic potential. There is kinetic energy because it's in motion. And there is some gravitational potential energy now because we do actually have a height. And now in the final phase, phase 3, the spring is going to be no longer compressed at all. It'll be going back up to its 0.3 meters. So we do know what that height will be. You can actually write that down here. Height is equal to 0.3 meters. Okay, and the book will, at the last second when the spring actually does reach us, the book may still be attached to the spring. After that, the book would probably fly off, but we're not 100% sure yet. We're not actually worrying about that yet. We're just saying what's actually happening in this process. And again, what is the reference we are using? We are going to be using this reference on the ground where H is equal to 0. So this is our point of reference. Okay, so with part D, it says represent the process with an energy bar chart. The way I see this is there's actually two processes going on. I believe it's actually just mentioning the process in part C, but it's good practice to actually draw a couple bar charts here because we do have two different processes going on here. First, we have the one where we are compressing the spring, so that would be process 1. And then we have the part where the spring is actually being released and the book is being launched off, and that would be process 2. So I think it would be beneficial to draw energy bar charts for both. So why don't we do that? So in this case, in part 1, we said that our system in this case is going to be the spring and the earth. Okay, so we said the spring and the earth. Spring and the earth. And in our second system, we're going to be saying that the system here now does not include the spring anymore. It'll be the book and earth. So there's two separate processes going on here, and of course the system is whatever you define it to be, but in this case this is what I'm going to go with, and we will try to work this out. So let's represent bar charts for these. So our first bar chart is we're going to worry about this first process here. So we start off with some gravitational potential energy initial, we have kinetic energy initial, we have gravitational elastic initial, we have some work, have final gravitational, final kinetic, and final elastic potential. So in this case, we said our spring doesn't have any mass, so we're not really worried about that. So our potential energy in this case is going to be 0. The spring is not moving, so we have no kinetic energy, and the spring is actually not compressed at all at this point, so we have 0 potential energy. Now we're going to compress the spring till we get to our final stage, which happens to be, for the spring, we're worried about right here, and we're going to have to do work because we're going to have to push that spring down over some distance. Spring is going to be resisting us. It says it's 0.3 meters, so we can have 3 blocks, each block for our distance, 0.1 meter per distance. Doesn't really matter how many blocks you use as long as we remain constant in our chart. So at the final stage, again, we have no potential energy, especially now because the spring is also on the ground, but we assume that it has no mass anyway. The spring is not moving, so there's no kinetic energy. And now there is actually potential energy because the spring is compressed, and it's compressed by the same amount of energy as that we had to do work to compress it. So that's why we have 3 bars here, 3 bars here, and that shows that we have energy is conserved. And that is also constant with our picture. In our second chart, this is now for our other system. This is when now the system is the book and Earth. And so let's draw a bar chart for this. Don't know why that came up. Okay. So let's draw a bar chart for this book and Earth system. So again, we have initial gravitational, initial kinetic, initial spring, work. We have final potential, final kinetic, and final gravitation, or elastic potential energy. And so in this case, the book is on the ground, so there is no potential energy, gravitational potential energy. The book is not moving, so there's no kinetic energy. And in this case, we're saying that the book is actually, the spring is not in the system, so the book does not have any potential elastic potential energy, so we'll say 0. And then in here, the book will we'll go to the final stage, and stage 3 would be our final. There is work done on the book. It happens to be done by the spring because the spring has this potential energy. And so consider that it does the same amount of energy here. So 3 boxes. In this case now, the book again is our system with the Earth. So we know there is no elastic potential energy in the book. So there is some height. It is moving at some speed. We don't know. We did actually say that this is the maximum point that the book could be gaining speed, because that's the maximum point of the elastic potential energy in the spring. So the kinetic energy will be at a maximum at this point. Like we said there's going to be this high kinetic energy. And after leaves the spring, the kinetic energy is actually going to be decreasing. So at this point, we're going to say that the kinetic energy is going to be higher than our gravitational potential energy, because we know that this kinetic energy at this point is going to be the highest that it can possibly be. So here the kinetic energy is bigger than our gravitational potential. We don't know by exact amount, but we do understand that it is higher, especially because it's also actually not that high above the ground, or our reference point, which is the ground. And we see that it is consistent because we have 3 bars on this side and collectively 3 bars on this side. So our final part, after the spring is released, how high will the book fly? So in order to do this, we may actually have to draw another picture and possibly another bar chart for this, and we will do that. So the book is actually going to, what's going to happen to the book after it gets past this. So we don't actually have to draw it again. We know these initial sequences. We can just maybe add a 4th step here. We can add a 4th step and say that when the spring is released, or after the spring's released and it lets go and it's no longer compressed, the book is actually going to fly into the air at some height, and it's actually going to stop at this point. Why is it going to stop at this point? We can actually draw a force diagram on this book, and we know that let's actually represent this with a dot. So when the book is at the top, what is going on here? There is the force that Earth exerts on the book, and then we have that's it. So at the top of this thing, we have this force that's going down, but it's stopped because the whole way while it's going up, the only force that's exerted is the force of the Earth on the book. So it's traveling in this upwards direction. Actually might be helpful to draw a motion diagram. It starts off at the ground. It's picking up speed. So it starts at the ground, then it picks up speed, and it's at its fastest point at the top of the thing. And then after it's no longer pushed by the spring anymore, then it starts to decrease and stops at the top. So that's all we're worried about here. So here's our multiple representations. We have a picture, we have a motion diagram, we have a force diagram. So what is the energy bar chart going to look like? So in this case, we're going to draw a thing where our initial position is going to actually be on the ground. Here's our initial position when it's on the ground. And our final is going to be up here while the book is stopped in the air, because we want to know how high the book will fly. So we want to know at its maximum position. So here's our final state. We know that based off what it's asking, and this is our initial position of what's actually causing it to fly that high. So let's make one more bar chart here. We have always gravitational, kinetic. We have elastic potential. We have work. We have final gravitational potential. We have final kinetic, and we have final elastic potential. So our energy bar chart here should actually look very similar to this, because this bar chart actually took into account our first position down here. Actually already took into account. So we should be able to get a similar thing. So we have that there is no potential energy because it's on the ground. We have no kinetic energy because it's not moving. We have no elastic potential energy because it's just a book. We're going to have some work that this spring does to our book, same as before. And then what about our final stage here? So we said that it's going to be at rest here. It's not moving. So we have no kinetic energy now. and we have no elastic potential energy. So that means all of our work has to be converted into gravitational potential energy. So 3 bars here, 3 bars here. We are consistent. We're consistent with our pictures. We're consistent with the conservation of energy. All looks great. So let's actually find out how high will the book actually fly. So we have an equation to write here. You can write it up here and then run out a little bit of space. So we'll try to improvise. So our equation here is that we have work done by the spring is equal to the final gravitational potential energy. So work is equal to mgh. So what actually is what energy is this work here? What is actually doing the work? We said it's the spring. And what do we know about spring energy? It is potential energy. So it turns out that the work being done here is very similar to 1/2 kx squared mgh. And so we can bring this down to here and solve for this. So we have 1/2. We have K is 80 newtons per meter. We have it being compressed 0.3 meters, so the change in x is 0.3 meters, and that's going to be squared. And that equals m of the book, which is a 0.2 kilogram book. 0.2 kilogram book. We have g, which is our gravitational constant, 9.81 meters per second squared. And then we have h, which is going to be in meters, that we're trying to find. So we are indeed trying to find this h, and once we do, we will have our answer. So on our left side, we end up with, take our calculator, we have 80 newtons per meter multiplied by our 0.3 meters squared. Actually, let me, got something here, which is actually kind of important. Always want to make sure we label everything, and so that our units are always constant. 0.3 meters squared. Okay. So again, we take our 0.3 meters and we square that. We multiply it by our spring constant of 80 newton meters, and then we multiply that by 1/2. So we end up with 3.6 newtons. And because this meters is going to cancel with this meter, so that's how we end up with newtons. So it's good to show our units. Actually, no, I'm sorry about that. See, that's why it's always good to show these units. It's not going to be newtons because this is meters squared. Okay, so it's not going to be newtons. It is going to turn out to be 1 newton is a kilogram meter per second squared. So since this is meter squared, we get kilograms per meter second squared. And that is equal to 0.2 kilograms times 9.81 meters per second squared, so we get 1.962. This is newtons, but meters, kilogram meters per second squared. times the h in meters. So divide this out, we get 3.6 divided by 1.962, and we get that our book ran out of room here, so let's just move this over, is going to come out to be 1.83 meters into the air. And that should be our answer.